Our next speaker is Omer Bar-Yohay, who is co-founder and CEO of Eviation. He founded Eviation Aircraft in 2015 and has been leading it as CEO ever since. Omer is a physicist with 15 years of experience in leading multidisciplinary teams of innovators and engineers in the fields of energy storage and electric propulsion systems in the global auto industry. His presentation is Eviation Aircraft, partnering to make it fly fast. Please welcome Omer.
Hey guys. I wanted to really jump into the details, but I cannot kind of let it go. I think Oshkosh, we have a problem. And I think the problem is that it's been my 5th consecutive Oshkosh event that talks about this. I see people in the room who's been here probably anywhere between 35 and more years. And I am sure that these things are being discussed again and again and again, and we're all sitting here waiting, wait a minute, when is this going to fly? When is this going to be certified? When is this going to sell? And we argue if it's going to be over a city or regional. I remember the first on-demand mobility 2015, that was the argument. We spent a half day. Do we go regional first? I think that we need to start shaking ourselves and listening to, you know what, think about it differently. When you fly the Atlantic for the first time in 4 months, building the Spirit of St. Louis, how many discussions were there about the certification process of going there? How many events like this took place? Talking about, damn, it's difficult to certify an aircraft. Yes, it's difficult to certify an aircraft. It's also expensive, and you're going to probably fail a couple of times. Trust me, we're really trying. I'm not sure we're going to make it. But you need to build them and you need to fly them. And I think if there is one kick in the butt that our industry needs, is the companies building them and flying them. In New Zealand, anywhere else in the world, you can make them in China if you want. Doesn't matter. It doesn't matter. It's the same kick in the butt. And I think this is really the call that needs to come out of rooms like this. And now I want to tell you what we're doing. But most of you know it already, so I'm going to do it quick. This works, right? All right, perfect. So Eviation Aircraft builds a regional all-electric. We do 9 seats plus 2 crew. We can fly 650 miles. That's normal miles. You'll see the 540 nautical miles in a second. Plus 45 minutes IFR reserve, and we do it at 240 knots at 10,000 feet. The technologies we did from scratch, and I'm going to agree with a lot of the presentations here. If you want to build electric, you have to build it from the ground up to be electric. Otherwise, it's going to be a crappy aircraft. We did it, of course, using ultralight materials because they're certifiable and they could be produced in a coherent way. And most importantly, because this way the whole thing doesn't weigh too much because we have this huge battery. And then we chose the best battery out there today. But as was mentioned here before, nothing, so I think it was Luciano that says our secret sauce is that we don't have a secret sauce. We just took the best battery we could find, packed it, and we fly it. That's it. Why? Because if we have to wait for the damn secret sauce, it's going to take years. And yes, we did it kind of autonomous. What's kind of autonomous? Kind of autonomous means you can fly this, you can remotely operate it, or you can let it be autonomous. But you know what? I don't care. It's your regulator's problem. That's the point. It's not going to be regulated as an aircraft, as an autonomous air taxi anytime soon. Why? Because there is no prevailing rule for it right now. There's not one in the foreseeable future. What is there? There are plenty of problems. By the way, also acceptance problems. I'm not sure I'm ready to go on an aircraft, turn right or turn left to look at the cockpit and see no one there. Not quite ready. And I do this for a living. So yes, we're building something that could be remotely operated. The business point of it, and I'll go exactly to that area of the presentation right now, because all we care about right now is business and go-to-market. When? And lights. We also care about lights. Wow. can we actually build this plane to work? Thank you. Ta-da! Anyway, so what's the purpose of autonomy if you want to go fast to market? Well, as was said here, I assume most of the territories will allow my airplane to fly with parcels, not with people. Why? Because it's damn hard to certify. And I think if there's going to be a Sputnik moment for this room, is 50 airplanes like this flying autonomously with parcels in some godforsaken area of the world. Why not? The next point of that is we want to see these planes self-arrange, meaning regional transportation is many things, but it's mostly seasonal. You fly from Boston to Martha's Vineyard, but only on Thursdays, maybe Fridays. No one flies Wednesday and no one flies Saturday, but you do fly back Sunday. How do you move your planes around? Well, with plenty of pilots and plenty of dollars. We want to change that. That's the whole point of autonomy for us right now. Why? Because it's possible in today's regulatory environment. Remotely operate, it's a weight exception for a drone. Let's go to work. What do we do and what's our timeline? Well, we will ground test at scale, meaning the full-scale aircraft with its passengers by the end of the year. We will start flying it with people around for the next Paris Air Show. That's why no videos, no pictures, no nothing. You want to see it? Come to Paris. 3 aircraft will be manufactured by the end of 2019 for the certification process. And yes, we do intend to do it fast. This is a mistake, obviously. It's 2021. It doesn't take 1 quarter to certify. But we are beginning certification in 2018, and we do intend to finish it in 2021. 1 quarter after that, we will have 2 launch customers operating. If we're 1 year wrong, that's nice. It's still really early. But this is more or less the plan to work. Who do we work with right now? These are the ones I can talk about. Despite the Siemens here, we did have a team go over to Australia to see the guys from Magnix, and they rock. So Siemens should watch their back. But they have started the Part 33 kind of earlier, so until you kick their ass, we're buying their borders. Honeywell, Hartzell, and ChargePoint. ChargePoint does the mobile charging solutions that we have. The Israeli Aerospace Industries is on board and helping. Kokum does batteries. Elma Design, less familiar maybe, does the cabin, and we'll talk about this a lot in a second. And Maniaghi Aeronautica, if you know them, an Italian company, does landing gear and other subsystems. Why did I show you this? Not because I wanted to tell you that I have plenty of people I can pay. This is the way I think you build an aircraft together. Why? Because no one does flight deck and fly-by-wire certification better than Honeywell. For sure not us. So we want to get the guys that know how to do it and get this past FAA to do it right. No one does Part 33 on something electric that takes 1,000 volts to 30,000 feet better than a company like Siemens. They did crash something in Hungary recently that could be a hurdle, but there are going to be plenty more of those. I can say this about a lot of the companies here, but the idea for us was when there is room to respect legacy in terms of going to the regulator, going to the solutions that actually work, we don't need to invent it. Let's get this done together. What does the plane do? So it's a big plane. Our takeoff weight is 14,000 pounds. As I said, 9 passenger plus 2, a maximum range of 540 nautical miles. By the way, that's after 3,000 flight hours on the battery, meaning that's at the end of your battery life. After 3,000 hours, we expect the battery to be thrown away. Flying into known icing conditions, this aircraft is built to give you scheduled flights. Nothing more, nothing less. Part 23, not too big, but still scheduled flights, flying out of places that, well, rain. Cruise speed of 220, that's the maximum range speed, most efficient. 260, less efficient, faster, you choose. We usually advertise somewhere in the middle, 240, but that's what we do at 10,000 feet. The aircraft will have 2 immediate versions. When I say immediate, that means they go to market together. One pressurized, one is not pressurized. Why? Because there is plenty of market for a pressurized aircraft and plenty of market for an unpressurized aircraft. That's it. The plane as it is more or less the same, some differences to fuselage, but the wing, which is what most aerodynamic engineers ask, yeah, the wing is the same. We do lose a bit for that. Stall speed is not too slow. We found that our customers actually like it. That means that if they do get to land in a big airstrip or a big airport for that matter, they can get into final or base or whatnot with the jets. They can actually get there fast. And our takeoff distance, that's for a 50 feet obstacle, is 2,600, which is kind of short. Sizes, yeah, you can see it. It's a big plane. 53 feet wingspan. If you look at the wingtip propellers and include them, you're at 60 feet. And it's a big plane. It does crazy stuff. And I don't want to go into all of the details of what this plane is like to fly, but I want to show this and I want to explain why electric through this. When you build an electric aircraft, you make it more efficient. We claim you also make it a cheaper solution for transportation as a whole, not only for general aviation kind of replacements. But what you also make when you do, let's say, distributed propulsion at that scale or a different scale, is that you give your design some new capabilities that we need to think about. And one of the most significant things when a pilot sees this aircraft, he's like, wait a minute, I'm doing banked approaches all the time. I fly out of those small airstrips. I don't always have the option to, take a different angle. That's what I get. So 15 degrees bank when you approach, well, that's doable. Can you do this with those wingtip propulsors? They're going to hit the ground. It's going to be a mess. One of the amazing things that happen when you have fly-by-wire and you can control your propulsion systems hundreds of times per second is that you can take care of all sorts of problems like turbulence, like what we'll see here as a crosswind, in a different manner. Because we have wingtip propulsors, you can do yaw with differential thrust, not with your control surfaces. But what happens if you do both differential thrust and control surfaces? You can get a clean side force. That means you can do as we called it, ZRCL, very catchy, I know, zero roll crosswind landing, meaning you don't need to bank your wings, and all you do is you do differential thrust and throw your tail in the opposite direction, and what you really get is the ability to take care of up to 10 miles per hour crosswind without any crabbing or any roll. That's landing in most conditions. The thing is, if you do this plus the angle that we do allow for a banked approach, you can actually exceed 30, and we're going to have the proven crosswind we're going to work with is going to be 35 miles per hour. So it opens up a lot of new discussions. And what I said before about turbulence is part of it. Think of the kind of augmented stability you could have if you only had the ability to control thrust and control surfaces hundreds of times per second instead of as fast as the pilot can jig a couple of throttles. So in a way, we have built this airplane as a fly-by-wire machine because we had to, because the only way to really govern 3 propulsor at these tips and get this done right is with a good fly-by-wire system. Once we did, there are plenty of features you can shove into that. It becomes a software problem, which is an interesting direction. You can talk about an aircraft like this without beginning to show really nice renders and pictures, right? So we're actually choosing upholstery right now, but I'll go to this area, which is more interesting. This is our cabin. It's a bit different than what you would usually find, but what is interesting, well, it's slightly bigger than the King Air 350, let's say. In most planes, the center of the cabin is, well, a bit taller, because this is where you walk back and forth, right? So what we did with the seats is that we allowed them to move a bit and tilt a bit so that you can get this effect, so that you can feel better when sitting in your aircraft. Now, You don't really get there before you build a mock-up and you say, okay, this is bigger than a King Air, it's probably fine, right? Well, it's not. It's really crappy to jump into these aircraft. And when we talk about acceptance and having millions and millions, maybe billions of travelers in all sorts of new machines coming up soon, I don't know if you guys, well, a lot of you are pilots, so that's not a good room to say this, but I know that you guys flew in small pieces before. But I'm thinking about my parents or the average American or average traveler as a whole. You put them in a Cessna 402 and you ask them how much fun that was. These planes jump, these planes are not comfortable. The average American of 1970 is not the average American of 2018, so they don't fit anymore. And the weight they can take is also a problem. So we try to take this into account. We build something really nice that gives you the look and feel of a business aircraft or a jet. What you see in the back is a toilet. Yes, we do have a toilet. And yes, we will take it out if you want more luggage room. What else can I tell you? This is what our airplane costs. It's $3.5 million today. By the time we do this continuously, with a few dozens a year plus, we'll be at 2.5. We expect it to arrive in 2022. This is what our airplane costs when operated 12 to 1,500 hours a year. This accounts for your direct operating cost. What you call here the estimated hourly rate does not include insurance, the cost of your airfield, and the cost of your pilot. Everything else is in. If you want to compare this to the prevailing market, the Tecnam P2012 Traveler is probably the cheapest aircraft of that size ever built. And the Pilatus is just a very successful aircraft, but a turboprop. We're dramatically cheaper than the turboprop, and we are cheaper than the Tecnam. But if you add the second, the right chart to this, and you understand that we fly nearly as fast as the Tecnam, you understand that actually in the terms of cost per seat per mile, the numbers here are mind-boggling. These are bus numbers. That's the promise of electric aviation the way we see it. Not flying over a city just yet. I would love to see it happen. I'm sure there will be great feeders for our products, but they're going to be late. The difference between what happens to oil and what happens to electricity, I'm sure everybody in this room knows, so that's boring. Thank you and see you in Paris is all I have to say, but I would love to take your questions.
Questions?
Anybody?
Sure.
I'm just wondering what happens when one of those wingtip propulsors fails.
Very good question. First of all, it kills the other one. And we can, I don't have the chart for this even in hidden mode, but this aircraft can climb from sea level roughly 300 feet per minute with all three propulsors. With only the tail, it can climb roughly 1,200 feet per minute. So we can definitely continue a takeoff while losing one of the wingtip motors and killing the other. Now, one of the things we need to think about, though, and this is going back to regulation and how do we certify this and so on and so forth. First of all, you need to show that this really works, right? So this is what we do right now. But when we as engineers sit and think about this, each of these motors, by the way, the Magnix motors, the Siemens motors, any motor that size, and we have 260 plus kilowatts at each point, is intertwined, meaning it has 6 phases. 3 phases can work roughly 75 to 80% of the actual power output of this motor in a failure situation. But usually they work together because the limitation of these motors is usually not the ability to take in current, it's the ability to take out heat. So what really happens is that an aircraft like this has 6 completely separate, independent motors. Inverters, controllers, the whole thing. You need 2 things to fail for a propulsor to stop working. So that's a very, very big, let's say, starting point as it is. Now, what I usually say is, yeah, you're right, this needs some fixing, and we do fix it. But you tell me the climb rate of a Pilatus when it loses propulsion, and we'll start fighting after that.
Not much yaw though when you lose a single engine.
Yeah, but again, 400 times a second, you wouldn't know. You literally wouldn't know.
Other questions?
Hi, Omar.
Hi.
So redundancy in the motor inverter sets is 6 independent. Do you have 6 independent batteries as well?
16.
16 independent batteries.
That is
and
correct.
you can remove them.
You can fly
one battery and 15.
You can fly the plane for, of course, a shorter period of time with 1/16 of its battery. It has 16 independent modules. Each can fly the plane.
Lock out 15, fly with 1. Land with 1?
Yeah.
Okay.
Go round with 1. Abort landing. That's the
Thank you.
real challenge. It's by the way, the solution for this is not some wizardry, just a huge battery. We carry roughly 1 megawatt hour, so our ability to exert a lot of power from what's left is still left.
We do something similar with the urban bus.
Yeah.
There's a number of batteries, and we can map out as many as are failed and continue on with whatever is not failed.
We do kill module. The flexibility it gives you in the design is the ability to kill modules when you have a thermal issue or what. If you're worried about a module, you can kill it and still complete your mission in most cases with the spare needed, because a lot of people are looking at these numbers and saying, okay, yeah, maybe, but if I would buy a Pilatus or a King Air or whatnot, I could fly maybe 1,500 nautical miles or maybe even 2,000 nautical miles. The question is, who the hell would fly for 4, 5, 6 hours in one of those cabins? And the answer is no one. And the real answer is, if there is one place where range anxiety just doesn't exist, it's electric aviation. When you go into your Nissan Leaf or Tesla, no one at Nissan, no engineer knows how fast you're going to go, how far, how cold is it outside, is it a bumpy road or whatever. When you go in your aircraft, well, I'm going to tell you exactly where you're going to land. I'm going to tell you exactly how much reserve you need. If it was a normal aircraft, you just wouldn't take as much fuel, right? That's the case here. We don't have a range issue. We just have a different plane.
Is this indeed the case, Omar, that you don't take all the batteries with you if you don't need them?
No, at the moment, and that's again a very good question. We could technically create this swappable situation where you take less weight. When working with our, let's say, launch customers, because again, I don't want to disclose the names of the actual operators, but our launch customers, while flying way shorter legs than what we can do, they care a lot about keeping their operational, let's say, cycle and their operational, they want to make this fit into their existing fleets. So they want to be on the ground for 15 minutes. They want to see, or maybe 25 minutes if they're crazy. They want to see very, very fast charging, and they want to feel comfortable flying roughly 10 periods a day without having to charge again and without coming even close to the IFR reserves or whatnot. So in most cases, it would make more sense to fly with the whole battery. We pay for it. We literally pay for it. I could get those great numbers, the $200 per flight hour, probably closer to $170 if you let me play with the batteries. But we don't do that. We just don't need to. The margins are big enough, the capabilities the plane gives us are big enough, are good enough, and I believe we won't need to see this until actual competition comes along.
I would have been very surprised if you told me that you didn't load all 16 batteries, but you implied that might be what you were doing, so I had to ask.
Good question, then.
Can you confirm, I heard you've been talking about batteries with 3,000 cycles.
No,
No.
3,000 flight hours.
3,000
That's roughly
flight hours.
920, maybe 910 cycles.
Okay. Thank you.
I was wondering, how do you see any potential synergies between the urban VTOL market and this kind of regional electric market?
I think there are 3 levels of synergy that we need to talk about. I think the first one has nothing to do with the tools. It has to do with the go-to-market, FAA, headache, social acceptance, how quiet it is, blah, blah, blah. In these senses, I love it that there are plenty of players around the table. I love it that there's plenty of money going with the hype here or hype there. Unfortunately for us, for a while, it's been the hype there, but we manage. And I think that whatever propulsion systems, whatever battery solutions, whatever safety, issues will be solved around vertical or around regional. It helps both sides. It needs to happen, and may the faster certification process win, more or less. So this is one, let's say, more strategic approach. In terms of the actual operations, I think we're going to see a lot of, I think that what we're building actually changes the way we live and commute today. Meaning you can live up in Ithaca, upstate New York, and work in New York City. Why? Because no one cares about your half-hour commute to a small airstrip not far from New York. Now let's find one. And then how do you do that it's not last mile, it's last 7 miles. Well, if you landed in any of the proper airports around New York City and you take Uber or the metro or, I don't know, you carpool with someone else, it's going to take you the time it takes, but there are a lot of options. I think one of these options soon enough is going to be flying. And I think those air taxis are going to happen. I think they're going to happen slower than most people would have wanted them to happen, but I think they're going to happen. The thing is, they already exist. We call them helicopters. They work pretty well, and they're kind of efficient. They only have one problem. They're a really, really complex machine to certify. They cost a lot of money. I heard some people call them some aircraft parts flying information rather than one aircraft. And I generally accept that notion, but I would say that making this electric can make it more accessible and can make it cheaper. We still have a lot to figure out in terms of the capacity of the skies. And the biggest example that we always give is Sao Paulo, right? Everybody flies into Sao Paulo every morning. 30,000 people go into their workplace every morning with a helicopter. That's actually true. But 3.5 million people go into Sao Paulo every morning. So with all due respect to the 30,000 that could afford the helicopter and the 100,000 that will be able to fly with our electric solutions, that's nice. That doesn't really put a dent into the transportation solutions of Sao Paulo or any other big metropolitan area. So I think there's room for everybody. Transportation is a huge market, and it needs disruption at so many levels that I think we can live together there very easily. I think the third part is, in part of the designs that you see today, you see all sorts of pods moving from one transportation solution on the ground. I think we've seen some of those from Terrafugia, and we've seen some of those from other companies working on this very, very seriously. And if you think about it, a pod that goes on my wings and V-tail and distributed propulsion, or goes on one of Terrafugia's solutions, or even goes on a metro, or on a train, or on whatever, I think we're going to see a lot more integration in the future. But if what I'm talking about is going to happen, I believe within the next 5 years, meaning you can buy a ticket, and if vertical takeoff and landing is going to probably start really working just 5 years after that. What I was just talking about in terms of the pods and integration and getting out of your house into a pod, and this pod eventually puts you in Australia in some suburban area, that's a while away.
All right, well, thank you.
Thank you, guys.